Okay, so now we're going to find the standard deviation from a sample. And remember, we had two options to choose from. And I'm going to use this one first. Okay, so we need to find our x values, which are right here. That's the 2, the 5, and the 8. Okay, and then we need to do the data value minus the mean. So we need to find the mean. So we're going to add all these numbers up, divide by 3, so 15 over 3 is 5. So I'm going to take each one of my data values, subtract it from my mean. -3, 0, and +3. Each one of these is a deviation. Remember, if we add all these up, they should come out to 0, which it does. Now we need to square it because of this 2 right here. So this would be 9, 0, and 9. If I add these up, it comes out to 18, which will be the top number. And then I need to find out what's my n, sample size. So I have 1, 2, 3 items in my sample, so 3 minus 1. 18 over 2, that's 9, which is 3. So the standard deviation for this sample right here is 3. Now let me show you using the simpler method. Okay, this one right here is actually the shortcut method, even though it doesn't look like it. So we're going to find our x values, which is still 2, 5, and 8. Then we're going to square them because of this x squared right here. So 4, so 2 squared, 5 squared, 25, and then 8 squared, 64. Okay, then notice right here, in front of that, which is, okay, x squared, right in front of this, it says add them all up. So we're going to add all these up. So the summation of x squared, that's going to give us 93. And then notice here, this is just x right here. Here's our x values. Right before that is saying add all these up. And that's going to give us 15. Okay, I need n, which I have 1, 2, 3 items, so n is 3. I can plug in. So I have 3 times 93 minus 15. And notice how this whole thing is squared. So this whole thing is 15, so I'm going to square 15. And then 3 minus 1. Okay, now notice that I'm not using the mean in any part of this. This is the reason why this is the simpler method, and it reduces the chance of error. Because if I go back over here and say I messed up and I got, we'll just say not a 5 but a 4 for some reason, well then this would be a 4, this would be a 4, this would be a 4, this would not be 3, that would not be 0, that would not be 3. You could check it right here to make sure it adds up to 0. But say you forgot to do that. That wouldn't be 9, that wouldn't be 0, that wouldn't be 9. So your mean affects this number, this number, this number, this number, this number, this number, which in turn would affect this number, which will affect this number, which will affect this number, and the whole thing just kind of blows up, okay? If you mess up the mean. Now this one, you don't have to find the mean, so you're not using the mean everywhere within the example or the problem, so there's a less chance of error here. Okay, so let's keep going with this one. Okay, so 3 times 93, that's going to be 279, minus 15 squared is 225. This is going to be a 2, so 3 times 2 is 6. Okay, and then 279 minus 225 is 54, divided by 6. That will be 9, which will be 3, which will be our final answer. Okay, so it doesn't matter which one you use as for this one, as long as you get the mean right. They'll come out to exactly the same standard deviation. Okay, now let's look at this. If we're at a traffic light at 3 different intersections and we measured the wait time 3 different times for each of these 3 intersections. Now, if I find the mean for each one of these, so 5 plus 5 plus 5, that's going to give me 15 over 3, so that gives me 5. If I do the same thing for this one, 4 plus 5 plus 6, divide by 3, so that'd be 15 over 3, still 5. And same thing for this one, it'll give me 2 plus 5 plus 8 will give me 15, divide by 3, still gives me 5. But notice the spread of this one compared to this one. This one has no spread, all the data values are the same. Compared to this one, it has a little bit more spread than the first intersection. Compare these two to this one has a little bit more spread. Okay, from 5, so that'd be the middle number here. That just happens to work out in this situation. It's not always the case. A little bit more spread out from 5, a little bit more spread out from 5. But notice that the mean didn't tell us anything about the spread. Okay, so the average or mean doesn't tell us anything about the spread of data, which you can call variation. It only tells us something about the center of the data. In order to represent the spread or the variation in data, you've got to use the standard deviation. Okay, so the average or mean just shows the center of the data. The standard deviation, that's the one that shows the variation of the data. Okay, now this one, say I give you a table like this right here on the exam, and I say, hey, go ahead and find the standard deviation. So what you're saying is, for this data value, there's only one of them. So I will take this data value minus the mean for that one. For 9.5, I have 2 of them. So I would do that twice. Okay? Or what I could do is, after I square my deviations, instead of adding this to itself, I can just multiply by 2 since I have 2 of these data values. And same thing for 10, I have 4 of them. So I'll have deviation squared times 4. The reason why we're doing that is it's based off of this formula right here. So here's a deviation, the x minus x bar. That is for one particular data value. So that's for one of these 9.5s. Since I have 2 of them, I would have to do that twice and then square them before I added all of them up. So this column right here is just looking at the x minus x bar for each individual value here, and they're only doing that one time. So if I added all of these up, then I'd be missing out on 1 of the 9.5s, 3 of the 10s, 3 of the 10.5s, 5 of the 11s, and 2 of the 11.5s. So what I need to do is take this column here and multiply by the frequency of that data value, and then it says add them all up right here. So you get this number. So then I can take this number and divide by n minus 1. Well, then I need to figure out how many data values do I have. And what you can do is come to your frequencies and add up all these numbers right here, which there are 20 numbers there once you add them all up. So then I can come over here, plug in this 9.7375, divide by 20 minus 1. So 9.7375 divided by 19. So that will give us, underneath the square root, 0.5125. And we'll square root that. And that will give us 0.7159. And that would be our standard deviation for this table right here. Now, if it said, hey, find the variation for this table, well, then what I would do is, if you notice, remember that standard deviation, you square that to get to variance. So if I square this number, which is the same thing as this number before it, the square root and the square cancel out, so the variation is actually the number that is inside of the square root before you square it. So that 0.05125, that's actually the variation. 0.7159, that is your standard deviation. Okay, your coefficient of variation, or we just call it CV, you would want to use this in 2 different situations. One where you have different data sets, or you have different means. So for the different data sets, you have 2 completely different data sets. One data set you looked at the heights, the other data set you looked at the weights. Whereas different means, you still have two different data sets, but both of them you looked at height, or both of them you looked at the weight, but they have different means within each of those samples. Okay, now this thing is going to have absolutely no units, and I'll show you why here in an example. This is your formula. These two things say the exact same thing. So this is your standard deviation for a sample, divided by your sample mean times 100%. This is your population standard deviation, divided by your population mean times 100%. So in essence, it's really just a standard deviation divided by the mean times 100%. It's just dependent on, did it come from a sample or did it come from a population? Okay, so let's look at this one. We'll go ahead and find out the CV for each one of these, and then we'll compare them. Because at this point, I can't compare inches to pounds. Those are two completely different things. So different data sets, I've got to use the CV for this. Okay, so the CV for heights. Okay, so 3 divided by 65. Notice how the units cancel out right there. That's why it has no units. Then times 100%. So this will give me 4.6%. And then we'll do the same thing for weight. So that's going to be 7 pounds divided by 175 pounds. Cancel out right there. Times 100%. That'll give us 4%. So which distribution has a larger standard deviation? And before I get to there, let's see which one has the more variation or spread. Now go back here. This is the coefficient of variation. Okay, so which one of these has more variation? Well, the one with the higher number. So that means that heights has more variation. If there's more variation, what does that mean about your standard deviation? It will be larger. So heights again will have a larger standard deviation. Now the standard deviation is good to use if you have a symmetrical distribution, but if you have a skew distribution, your standard deviation is going to have two different results. So say you have something like this right here where it's skewed. The standard deviation in this little section here is going to be different from this standard deviation over here. Therefore, no single number could describe the spread of this distribution right here very well. So only use the standard deviation if you've got symmetrical distributions, not for skewed. Instead, if you're looking at a skewed distribution, what you should be looking at is the first, the second, and the third quartile. Remember, median is the same thing as the second quartile, the smallest and the largest data value, which, if you remember, we use those 5 numbers to construct a box plot. So if it's a skewed distribution, you need to use the box plot. If it's a symmetrical distribution, yeah, you can go ahead and find the standard deviation. Okay, something that is super important in this class is something called the empirical rule, or you could call it the 689599.7 rule. I just stick with the empirical rule, shorter. Now the first thing that has got to happen is if the data set is normally distributed, remember that looks like this right here, it's a bell-shaped curve, then I can apply the empirical rule, which says that within one standard deviation of the mean, we are looking at 68% of the data. Within 2 standard deviations of the mean, we're looking at 95% of the data. Within 3 standard deviations of the mean, we're looking at 99.7% of the data. Now, if your data falls within the 2 standard deviations, we call that data usual, or we would expect that to happen. But if it falls outside of the 2 standard deviations, it will be labeled as unusual. And anything outside of 3 standard deviations is not likely to be seen.